Welcome to our introductionary on malware detection with convolutional neural networks. We will focus in this section on building a binary classification model with the help of convolutional neural networks. This algorithm is quite popular within computer vision related algorithms and widely also used to build image classification models. You will for sure ask yourself how image classification is relevant for building malware detection algorithms. Well, you will see how flexible convolutional neural networks really are, and hopefully this section will benefit you to build your data science portfolio. We will give you an introduction on the popular framework Pytorch, an API developed by Facebook. Then we will have a look on how convolutional neural networks can be applied for image classification problems. We will apply what we have learned on malware image dataset in order to build a robust binary malware detection classifier. By the end of this section you will be able to build a malware classifier based on image classification approach. In this chapter, we mention to the popular framework Pytorch in order to enable you using neural networks for solving real-world cybersecurity-related problems. Pytorch is gaining more and more popularity, and recently, it seems that Pytorch is able to overtake the other popular deep learning framework TensorFlow. Basic as well as advanced Pytorch skills are outlined more and more in job descriptions related to data science. Developed by Facebook, you can install the Pytorch framework and find various installation guides in the internet. An installation description is not part of this tutorial. We would like to encourage you to take advantage and learn Pytorch. We hope that this little Pytorch tutorial can help you to get a solid understanding of this popular deep learning framework. What is deep learning? Deep learning is the process of creating and training a neural network algorithm to learn the relationship between input variables and their associated output variables. This relationship arrives at acceptable accuracy through an iterative process of hyperparameter optimization. What is a tensor? First we need to understand and differentiate what a scalar, vector and matrix is. A scalar is a quantity, which is described by a numerical value or single element and can be seen as a zero-order tensor. For example, x equals torch, dot, tensor of scalar 1.5. Here we would like to understand different outputs for following commands. Dot size, returns size of tensor, the returned value is a subclass of tuple. Dot dim, returns number of dimensions. Numil, returns total number of elements in the input tensor. So, for the scalar of 1.5, the dimension is 0 and number of elements is 1. A vector is a one-dimensional tensor and has one axis, thus it can be seen as a first-order tensor. X equals torch, dot, tensor of vector, 2 and 3. The dimension of this vector is 1 and number of elements is 2. In order to access the elements of the vector, indexes are required to be put into square brackets. A matrix is a rectangular array and has two axes, thus it can be seen as a two-order tensor. For our example, x equals torch, dot, tensor of vector and then two axes in square brackets. In order to access element 10 by using square bracket open 1, 2, where 1 describes the index of the tensor of order 2 and 2 describes the index of the element within the tensor of order 2. It is important to view a second-order tensor as a tensor that is being built from two first-order tensors, for example twice square bracket open, tensor of order 1, square bracket closed and square bracket open, tensor of order 2, square bracket closed twice. The dimension of the matrix is 2 and total number of input tensors is 6. And finally, let us shed light on an example with tensors. A generalized representation of vectors and matrices can be described as tensors. For our example, x equals torch, dot, tensor of vector and then 3 axes in square brackets. In order to access element 10 by using square bracket open 2, 2, where 1 describes the index of the tensor of order 2 and 2 describes the index of the element within the tensor of order 2. It is important to view a second-order tensor as a tensor that is being built from 2 first-order tensors, for example twice square bracket open, tensor of order 1, square bracket closed and square bracket open, tensor of order 2, square bracket closed twice. The dimension of the 3-order tensor is 2 and the number of input tensors is 9. Tensor can have more than 3 orders and Pytorch enables us to use more than 3-order tensors. We have learned so far, basics how tensors work, and now we would like what numeric types we can store in a tensor. For a number of reasons, Pytorch does not support Python numeric types. To begin, performing large mathematical operations on large quantities of numerical data in Python is slow in comparison to code written in a compiled programming language. Second, Python lists are one-dimensional, and operations such as vector summing and vector dot product are not defined. Finally, a floating point number takes 32 bits to be represented on a computer, whereas Python converts integers to Python objects, causing performance issues when processing tensors. Pytorch supports setting the value types, integers or floating point values, that tensors can carry with the d.type parameter. Now we have a better idea what tensors are, we can understand basic operations with tensors. .add means that 2 tensors with same dimensions are added. .sub means that 2 tensors with same dimensions are subtracted. .mul means that 2 tensors with same dimensions are multiplicated. So here, you can see an example with 2 tensors, A and B, and basic operations with tensors. Operations can be done within Pytorch to process data. So now we would like to understand how vectorized operations can be done. Torch.add is addition, torch.sub is subtraction, torch.mul is multiplication, and torch.div is division. Pytorch is a tool for creating neural networks that is both transparent and easy to use. Pytorch provides a high-level functionality called layers to isolate the high-complexity architecture of a neural network. Input layers, hidden layers, and output layers are all often employed. Only one input layer is employed, and its form is determined by the training data. The number of units in the input layer should correspond to the number of features in the input data. For neural networks, at least one hidden layer is utilized. The number of hidden layers utilized depends on the complexity of the data issues. One output layer is used to form neural networks in the same way that one input layer is used. Between the number of units in the input layer and the number of units in the output layer, the number of hidden units need to be set. The anatomy of a layer consists of input data, transformations and output data. A deep learning training process consists of building the architecture, model accuracy evaluation with loss function, and finally optimizing weights of the neural network. There exist linear and non-linear types of layers. Linear layers apply a linear transformation. As neural networks consists of multiple layers, just stacking multiple linear layers will not have a learning impact on the neural network, as neurons will not have linear relationships. So basically non-linear types of layers will be used in Pytorch, for example like sigmoid, ReLU or tanh. A sigmoid activation function maps inputs to outputs with a number in a range between 0 and 1. This function is not widely used in neural network architectures. This model is more suitable for binary classification problems. The disadvantage is that for binary classification, the output of sigmoid is close to 0 or 1, the gradients for layers before sigmoid function are nearly zero, so the parameters of the previous layer get gradients close to zero and weights are not optimized. A tanh activation function takes a real value number and outputs a number in a range between -1 and 1. Similar to a sigmoid function with the same shape and centered around 0. Anyhow, both S-shaped activation functions are not used widely today within neural networks. The main problem is, in case a very deep neural network need to be trained, the gradient need to propagate backwards throughout the network starting from the end. The issue here is that a chain of activation functions like sigmoid of a sigmoid of a sigmoid of sigmoid etc. is used, and finally a multiplication of derivatives of activation functions is done. When you multiply a chain of small numbers, you will get even a smaller number. So the result is that weights closer to neurons are not trained at all within very deep neural networks. In recent years, a ReLU or rectifier linear unit activation function has become more widely used, as tanh and sigmoid are not very suitable to be used. As you can see, values and thus gradient is greater than 0. The optimizer will find the right set of weights sooner, and thus the training process is faster. By using the ReLU activation function, a learning rate need to be carefully modified to avoid that the activation function becomes non-responsive. By using a leaky ReLU, derivatives will be always positive, and it is still a non-linear function. Another activation function, which is getting more and more attention recently, is the hard tanh. This function has an output between -1 and 1 similar to the tanh function, but has a hard ramp version of tanh. There are other more activation functions available in Pytorch that will not be covered here. The Torch.nn is a Pytorch submodule for artificial neural networks that contains all modules for building various neural network architectures. As characteristics, a module can have parameter instances, which are tensors whose values are optimized throughout the training process. We have several subclasses, such as sequential, which is later used to design basic sequential layers of a network. Another subclass is linear, which will be used later as well. Two methods for developing neural network are offered by Pytorch. First, we want to introduce you to the previously stated sequential class, which creates a predefined series of operations for building a neural network. Now, we import the required Pytorch libraries including Torch.nn module. We next begin to set up our sequential class and perform operations of the neural network in the sequential class established. Our first operation is n.linear with two arguments, input and output features. Input feature is size of input, and output feature is size of output. Three arguments are allowed to be used with linear. It is number of input and output features and whether the linear model includes a bias or not. Let us see on our example how this is implemented in Pytorch. Within a neural network, the dot product of the weight and the input variable vector must be translated into a nonlinear output as a further step. The rectified linear unit is a typical nonlinear transformation function used in neural networks. Now, we can compute the next layer with linear operation and take the outputs of the first layer as input features for the second layer. Finally, all outputs of neurons will be transformed within a commonly used function, the sigmoid function, to get a binary classification among two classes. Another, maybe more straightforward and transparent method of creating a neural network in Python is to use the nn. Package. Neural networks are the focus of this module. By defining a Python class and two methods, the init and forward methods. The init method manages the input operations of neural network layers, the forward method manages a reasonable data infrastructure as activation functions based on the init method's stated operations. Within the specified classes, a parameter self is used for every method, and methods and attributes can be accessed by using the phrase self. Within the neural network's init method, a Python super function must be specified to execute code contained within the init method. So we can use NN module class. In the first line of the new init method, we call the super function with the class name and self. We save layers within the init method, which are declared as self attributes. Layers defined in Pytorch as properties of self are saved within the init method layers. We have two n.n linear layers in our case. One of them contains input variables for two nodes in the neural network layer, while the second leads to the output node. Within the init method, we save layers that are declared as self attributes. Now let us see the example. We store the operations for our example neural network as attributes inside command self. Another implementation which is required is the forward method. This method takes two arguments, one is the self argument and the x argument as a placeholder for our real data. So consequently the first step is to pass data which is represented by the x argument to the first operation, which can be done by self.operation 1 of argument x. While using the Pytorch functional interface, we can pass the output of this layer to the nonlinear ReLU function by using torch.nn.functional.relu.self.layer1 of argument x. After layer 2, the final output is passed to the nonlinear sigmoid activation function. And now we can define the forward method. To get access to the neural network, the defined object class will be addressed to a Python variable myNetwork. Machine learning for malware detection is still in its early stages, and adoption of deep learning to detect malware is gaining more and more importance, for example antivirus software development. This project is considering deep neural networks for classification of malware. A widely used algorithm is convolutional neural network, which is very effective for image classification tasks. But how can an algorithm built for image classification be used for malware detection? Well, an approach is to convert a malware into an image. You can find many converters and pieces of codes to convert binary values to images in the internet. For our project you can download the training and test datas. First, let us take a look how convolutional neural networks work. Generally, we can understand that neural networks with more than one convolution operation is called convolution neural network. Generally, we can understand as inputs for convolutional neural networks natural signals coming as multidimensional arrays. The usage of convolutional neural networks is not limited to computer vision tasks. For example, one-dimensional convolutional neural networks can be applied to time series analysis, test and sound processing and so on. For computer vision tasks, convolutional neural network or CNN are applicable due to the following reason. CNNs consider correlation of nearby values in arrays, thus probability that nearby color pixel values are same is given in images and videos. CNNs are robust to variations of feature locations due to pooling layers, which will be described later, thus location for object detection or classification is irrelevant. For simplicity, let us assume that we want to build a neural network model that can classify wolves in images. A wolf has certain features that provides the unique signals to the neural network like legs, nose, eyes, ears and so on. Inputs for convolution neural networks for image processing are numerical values which are arranged as height, width and channels or features. Each image provides a probability score belonging to a defined class. In case a feed-forward neural network is trained for image classification, there exist some essential roadblocks to consider. First, flattening an image to an one-dimensional vector results in the loss of spatial information. Closely spaced nodes are critical because they contribute to the definition of an image's characteristics. So we need a way to use spatial correlation of image features to see the wolf in our picture no matter where it is. Another disadvantage is, when working with large images, the number of weights quickly becomes unmanageable. For example, there are around 150,000 weights to be trained for a 224 by 224 pixel image with 3 color channels. This creates problems while training, and overfitting can take place. A feed-forward neural network uses simple matrix multiplication as its core operation in its linear layers to describe interaction between input and output units. Thus every input unit interacts directly with the output unit. Each element of the weight matrix is used only once. A convolutional neural network is using same weights in multiple convolution layers, which can be understood as parameter sharing. From input units to output units, a filter is transforming meaningful features. Fewer parameters and memory is therefore required compared to neural networks. Let us have a simple comparison of neural network with dense layers using matrix multiplication and convolution layers using same weights. Three main components for a typical convolution neural network are convolution layers, pooling layers, and fully connected layers. Within convolution layers, features are learned by deep neural networks. Then convolution neural network will look what features are present in an input image and finally produce specific activation vectors. These patterns are initiated by fully connected layers within the convolution neural network. In case if the image is a wolf, activation pattern differs of that of a cat or dog. Let us first get a better understanding how convolution layers for image processing work. For three-dimensional convolutions, input data has a shape of a tensor in form of channels, depth, batch size, height and width. For example, number for channels for a colored image is sum of red, green and blue. It is 3. The output shape of a convolution neural network consists of batch size, and the other data will change by using filter, kernel size and padding. Convolution operation is done for all different spatial localities in the input volume. The convolutional layer extracts different features from each part of an input image. This layer performs a dot product between two matrices, where one matrix is the set of learnable parameters, also known as a filter, and the other matrix is the restricted portion of the receptive field. The filter assigns weights and biases to any area of the input image. For instance, a 3x3 filter would represent a 3 pixel by 3 selection of the image. By using filters, number of weights which are calibrated during training process of a neural network. Convolution filter values are continuously updated as the network is trained. Edge detection and sharpening are basic feature extraction operations by a filter. The kernel or filter, which is 3x3 or 5x5 in size, slides across the height and width of the image, producing the image representation of that receptive region. This produces a two-dimensional representation of the image known as an activation or feature map that gives the response of the filter at each spatial position of the image. The sliding size of the kernel is called a stride. Finally, the activation or feature map is taken through an activation function. The activation functions can be a ReLU, sigmoid, softmax and many others, which are used to decide whether a certain feature is present in a given location in an image. More filtering layers can be added for deeper CNN. Now, the pooling process comes into consideration. Spatial dimensions of each activation map is reduced by pooling while aggregating localized spatial information. The pooling process squeezes the output from hidden layers along height and width. The most popular pooling process is max pooling, which reports the maximum output from the neighborhood. Additionally, pooling supports averaging, minimization, and conversion to another function. In this case, the pooling layer collects only data that has been aggregated using a specific aggregation function. Its task is to reduce the height and width of the matrix by half while leaving the depth of the matrix intact. Because of this procedure, we are able to reduce the risk of overfitting by identifying the most influential characteristics of our pooling layer and train the model faster. The data from the last connecting layer is the input of a fully connected layer. The FC layer is responsible for flattening the vector value. A fully connected layer takes the output of the convolutional layers and combine it through learning of nonlinear combinations of high-level features. It helps to map the representation between input and output. The fully connected layer is learning a possibly nonlinear function in that space. The final layer is in charge of calculating the probability of belonging to a given class. The softmax activation function is used for multi-classification. The sigmoid function is used for binary classification. Padding. What happens at the edges of the image is a good question to ask yourself right now. When we apply convolutions to a normal image, the resulting image is downsampled by a factor proportional to the filter size. What are our options if we do not want this to occur? We can use padding. Padding equalizes the size of the feature maps produced by the filter kernels with the original image. Padding is very useful if the edges of a picture have significant functions that must be taken into consideration during the model training. Backpropagation. After we defined a neural network architecture, we need to understand the performance of the network and finally optimizing the network. A deep learning model is trained by optimizing its parameters, much like any other parameter-based machine learning model. Backpropagation is used to tune the parameters, and the final or output layer of the neural network returns a loss. So first let us try to understand briefly what backpropagation is. The neural net training process's goal is to identify the weights, W, and biases, B, that minimize error. The gradient descent algorithm does it. To begin, the weights are randomly initialized, and then a process of iteratively changing the weights is undertaken until convergence. Each iteration begins with a forward pass in which the current prediction is produced and the model's error is evaluated using a loss function. Using gradient descent and the chain rule of differentiation, this loss is then backpropagated to the preceding layers. Thus, a backward pass is used to calculate the weights gradient. To reduce the loss, the parameters or weights at each layer are adjusted appropriately in order to find the minimum point of the loss function, where the gradient is 0. A coefficient ranging from 0 to 1, often known as the learning rate, determines the level of alteration, and the algorithm iteratively moves in the direction of the steepest descent toward the minimum point. The scalar learning rate is a hyperparameter which needs to be tuned. The optimization schedule, which is the process of changing the weights of a neural network, has a substantial influence on how successfully a model is trained. There are many variations of loss functions depending on the particular task of classification or regression, and Pytorch addresses all of them. As we are creating models for classification tasks, I will give you a brief introduction on loss functions for classification. Stochastic gradient descent was developed in response to the constraints of gradient descent in order to address performance difficulties and accelerate convergence in huge datasets. Probabilistic approximation of gradient descent is stochastic gradient descent. Because, at each step, the algorithm calculates the gradient for one observation taken at random, not the full dataset. Stochastic gradient descent requires just that the predicted value of the random observation be a subgradient of the function at point W. In large-scale datasets, stochastic gradient descent is more quicker and better suited. However, since the gradient is not computed for the full dataset, and instead, is only applied to one random point on each iteration, the updates have a greater variance. When compared to gradient descent, This causes the loss function to change more throughout each iteration, making it more difficult for the algorithm to converge. First, let us understand what entropy means. Entropy is a term used in information theory, so basically we will try to give you an intuition what entropy is. Let us see what is scenario 1. You have a bag of 3 balls. One is black, one red and one green. The goal is which color has the fewest questions. Next, scenario 2. You have a bag of 2 balls. One is black and one is green. Now let us calculate the probabilities of both scenarios. Probabilities picking each color can be multiplied as they are independent but more suitable to sum them. Our conclusion is that with multiplication of different probabilities decreases the end result, so entropy is much more suitable. The more question is required to find the correct color, the more uncertainty exists, thus entropy is higher. And the formula entropy can be seen here. Next, we take our example with image classification of cat, wolf and dog to understand cross-entropy. A machine learning model predicts the likelihood of each data belonging to each class label, which is between 0 and 1. Cross-entropy measures the difference in entropy between two probability distributions over a random collection of events. When projected probability differs more from anticipated probability, cross-entropy loss increases. When projected probability differs less from anticipated probability, cross-entropy loss decreases. So generally, we can differentiate between expected probability P and predicted probability Q. The cross-entropy formula considers two distributions Px target probability and Qx actual probability into consideration, defined over the variable x. Let us say a model predicts if a wolf is recognized in a given picture and the probabilities y are 0.1, 0.6 and 0.3. Sum is 100%. Probability 0.6 is labeled as 1, the other two probabilities are labeled as 0. Cross-entropy can help us here, in which direction the parameter of a model needed to be tweaked to get finally a good model. We now understand how to build artificial neural networks in Pytorch, and we have a better understanding on how convolution neural networks work and can be applied to image classification problems. Now, we can apply the previous theoretical background on neural networks on a dataset to build a malware classifier based on convolutional neural networks. During the final part of this video, the MNIST dataset is used to understand better the object-oriented approach to build neural networks in Pytorch. The dataset which we want to build a robust, deep learning model can be found in the repository. Let us get started within Google Colab to create our deep learning model for malware classification. First, let us create our necessary environment by downloading basic libraries in order to kick off creating our classification model. We install Torch and Torch Vision libraries, pandas, numpy. We will also later use Tensorboard to install the necessary packages to run Tensorboard within the Colab environment. The image files containing malware and benign data will be uploaded to the Google Drive and finally mounted within Google Colab on a defined path for further usage. 80% of all the data will be used for training and the remaining 20% will be used for validation. Here we will define the different path to our training and validation data. Let us have a quick view on the distribution, how many images are for training and for validation. Image files will be resized and normalized. Pytorch transform operations for data augmentation offered by Pytorch is recommended to be applied for images. Now we would like to begin to build our convolution neural network in Pytorch considering Pytorch modules, there are different ways to build the convolution neural network. Here we want to focus on the object-oriented method, as also shown at the beginning of this video. A four-dimensional filter of the kernel is the main parameter, which includes number of input channels and output channels as well as kernel height and width. Usually kernel height is same as kernel width. A conv2D is used and not conv3D because color dimension is not a spatial dimension. Pytorch models are based on modules, and module is base class that all other modules inherit from. For example, a sequential module inherits from module class. So we can summarize that a sequence of modules can be a model. Thus custom models will also be models which inherit from module class. For example, the linear module inherits from the module class. Interface of convolution layers and dense layers in a neural network is flatten. Output of conv2D layer is image and input for dense layer is a vector. Let us first build an example with the MIST dataset to understand modules and convolutional layers. A simple model is built with the sequential module, a linear layer, followed by ReLU, followed by another linear layer and again ReLU, and finally linear layer with log softmax activation function. So let us see how a custom model will most probably look. First, a class is defined that inherits from nn.module. Layers are then defined inside the constructor, the 3 linear layers and 2 relus. Within the forward function, operations are defined by the layers that are created before. So as next step is to build our convolutional custom model. We build a sequence of convolutional layers, ReLU, max pool layer and fully connected layers. In the prediction class, all necessary operations are defined. Parameters used for convolutional neural networks are for the first sequential layer. For instance, number of channels in the input image, number of channels produced by the convolution, size of convolving kernel, size of convolution. As our MIST dataset is a grayscale image, the input channel is 1. A kernel with a size of 5 by 5 matrices needs to be created. To conduct the convolution, all we have to do is move the kernel horizontally and vertically along the picture, then do a dot product with the kernel, and a small section of the original image. The next sequence layer consists of a convolution layer taking over the previous output channel as input channel of size 16. Okay, so now we have a deep understanding on how modules and classes are built within Pytorch around convolutional neural networks. We now approach on our convolutional neural network for malware classification. We define 5 convolutional layers and 1 max pool layer as well as 3 fully connected layers, and finally drop out for optimization purposes. We use the GPU of Colab to train the model. Tensorboard allows us to have an excellent visual view under graphs on the model architecture in terms of layers and input-output relations. Therefore we define the necessary arguments to display the graph of our convolutional neural network in Tensorboard. Let us try to get a better understanding and overview on the used parameters. Alright, finally, we define a function with parameter ranges for dropout, learning rate, batch size and shuffle, which are applied later for model training and hyperparameter tuning on the training dataset. What can we understand as batch size? A batch size is the quantity of training data samples pushed through the neural network in a single iteration or forward pass. We consider to test 32 64 and 128 as batch sizes to gain maximal accuracy and minimal loss with our training data. Additionally, we decide if the data samples in the training data loader is shuffled or not, but generally it is highly recommended to shuffle data. The neural network is continually learning and adjusting its weights. Splitting training data into batches and shuffling is very helpful. Consequently, each batch trains the network sequentially while taking into account the updated weights from prior batches. First, we need to define a function for hyperparameter tuning of our model, which will be used on the available training dataset. This for loop takes, as previously outlined, different parameter values for batch size, dropout as well as learning rate and shuffling training dataset into consideration to find the best parameters. We will use the Adam optimization and cross-entropy loss function. One pass through the full train set is referred to as one epoch. So here we use 10 epochs for model training with training data setters for loop. Overfitting can occur if too many epochs are used because the network has been learning from training data for too long. Then again A for loop, we iterate through all the batches from train loaders starting at index equals 0, where the batch number is I and data is a list of images and labels. A necessary step is to zero out the gradients with optimizer 0 grad, otherwise all the gradients from multiple passes will be accumulated. Here we define our Tensorboard related right arguments for parameter visualization, which is loss and accuracy. Finally, we print for every single epoch the current state of the defined parameters like learning rate, dropout and batch size. And also loss and accuracy will be printed out for every epoch. At the end, referring to our first loop, we reflect the calculated hyperparameter values within Tensorboard by using the righted params. And now let us train and afterwards create our Tensorboard. Tensorboard. The first click on the Tensorboard menu item H params, and have the overview of all different hyperparameter combinations. Tensorboard gives us the opportunity to download these hyperparameter combinations in different formats. You can have also an overview of the training process regarding the hyperparameter combinations. Within the submenu item, Parallel Coordinates View, it is possible to have a visual overview of different hyperparameter settings applied for training data. We can focus on relevant parameters having an impact on high accuracy and low loss. We have identified finally a dropout of 0.5, a batch size of 128, a learning rate of 0.001 and shuffle equals true. We then adjust the batch size to 128 by loading the training data validation dataset. Then we adjust the dropout value to 0.5 within our neural net. Bring the model to device. Set criterion, optimizer with learning rate 0.001 and fire on the scheduler. And finally we start to train our model on training and test data. Our malware classifier based on convolutional neural network has a good accuracy for training and especially for validation data. We can be confident that this model is robust and accurate to classify malware based on binary image classification. The binary classifier has an accuracy for training and validation data above 97%, which is excellent. We hope you enjoyed this section.